Well, good morning. I'm pleased to be talking here today. And so the talk that I have today is actually emerged as a couple of different topics that we've been working on. And so they come together as a theme. And I thought that would be good to talk about them together. So the title of my talk is A Bigger Picture of Secure Multi-Party Computation. And I'll talk about a couple of different angles and you'll see why, I say that we want something bigger. So generally, you don't need an introduction to secure multi-party computation. Everybody here understands what it is. And I just wanted to say that, we think of data that is distributed across multiple different sources. And it's so private, we would like to compute with this data securely. So I would like to use this as a running example throughout this presentation when we say that, for example, there's a number of different hospitals. So let's try to use the pointer, but I guess it's doing something else. And so we have a number of different hospitals that say have a few patient records for some rare disease, and they cannot necessarily do proper analysis locally, so they would like to collaborate. They would like to protect their data, enter them into a joint computation that is going to be done by those nodes in the middle who process the data, analyze it, and say, for example, what they would like to learn is what is the most effective treatment for that condition. And the result is going to be delivered to some designated parties. And this example is going to be the node on the bottom left. So this is just something to illustrate different components of the computation that we're going to be using today. And so in general, there's been a lot of focus on how we do this, on the techniques themselves, which is well justified, right? We want these techniques to be as fast as we can. We looked at different security models to make sure that the security guarantees are strong. And so over the many years, I guess, 4 decades, the advancements were significant, right? So there's a variety of different approaches, and sometimes it's difficult to even understand which approach is going to be the best in different settings. There's the speed has seen great improvements. We're talking about orders of magnitude, even for techniques that conceptually seem the same. And there's also the amount of communication has been reduced significantly, so the speed went up. But another important part is that we started with no tools, and maybe fair play, and 2004 was the first tool, and now 20 years later, we have a variety of different implementations, compilers, tools. There's a lot, right? There's like new companies that are working and sort of trying to deploy these kind of solutions, so the progress is enormous. But what I'd like to say as a part of this talk is this is not the full picture of what we should be looking at. And in general, if you go back to this figure, what the focus on the techniques themselves is basically how we run the computation itself. So in this case, it's highlighted basically the protection mechanism, how we enter data into the computation, how we run the computation, but clearly looking at this figure, that's not the full picture. And so what I'd like to look at a couple of other components that surround secure computation and see what we can do in that space. And the first one will be the inputs, right? So traditional inputs are out of the scope. We say input come in somehow into our computation, and we're going to be working with whatever we got. And so this is, in general, difficult to do something with the inputs for a reason, right? We don't know what the inputs are. They're private. If we knew what they were, we wouldn't need them in the first place. So there is no necessarily universal solution to make sure that the inputs are good, right? In some particular sense. But nevertheless, if somebody modifies inputs, tampers with them, the consequences can be devastating, right? And I would like to, give this simple example. Probably a lot of people already know in this audience, saying that we're computing the average salary of people in this room. Everybody enters their salary. I say my salary is 10 million. We get the result, and everybody's like, oh, I'm so underpaid. And so, like in this example, not only everybody is denied of the true output, but what's worse is that I can actually undo my tampering with the inputs and I can learn the actual result that everybody else doesn't get, right? So in some way, it's like denial of service for everybody who's participating in computation, except that they don't know. It's more like a deception, right? I get the result and everybody else doesn't. So in this particular case, what we're looking at is a different component of secure computation. We're saying that the inputs themselves somehow are not validated or not verified, and there's no single solution, right? Admit this is a difficult problem, but still something I believe that in certain contexts we can do more than just take the inputs and accept that we can't do anything. And so what would like to look at is say, one simple solution is always possible, right? The inputs are supposed to be in a particular range. Like you're not allowed to enter negative salary, for example, right? And within the computation, we can check for, those sort of discrepancies, and that's simple. Another one is here, I'm looking at input certification. This is information that would be possible to verify in certain contexts. And if we're talking about some credentials that obviously they can be issued by the government or some other entities, and we know, for example, the age, could be verified. Your income could be verified if it comes from the employer, for example. So for our example of salary, you can actually make sure that what you're entering is data that's been approved by the employer that you work for. And in general, I would like to think of what else can we do as a community, right, to somehow prevent this issue of input tampering and mislead people in the computation. And what I would like to use as a motivating example, say, even if we talk about the context of certified inputs, is verifying that, say, a business sort of complies with the sustainability practices that they claim they are. So in this particular context, saying that, for example, I have a business who would like to get the certificate or label saying that we're following sustainable practices. But in general, there's no necessarily verifiability or accountability because in some way that means checking exactly the details of their businesses, sort of sensing their electricity, say utilization, right? Their sort of chemical use and all of that values, basically all of this data that can reveal a lot about the business and maybe proprietary information. So that seems like would be a good place for using secure computation, but the computation itself can be pretty simple. So what we will need to do is just to make sure that you're complying with the policy. But the issue is that, how can we trust that what they enter is actually correct data, right? They're incentivized in this case to get this label saying that I'm sustainable. So in a way, we would like to make sure that when we get the data from a sensor, yes, we cannot see that, but we can trust that it actually came from an authentic source and that's the correct data. So what we've been looking at in this space is trying to do certification in combination with secure computation faster, right? So we know that it's possible, say, to go through commitments. So you have a signature, you go through commitments to connect it to secure computation, and that's been done before. I think the challenge here is that we're combining computationally secure techniques, say, like signatures that operate over a large space. And on the other hand, if we have, for example, secret sharing, that is information theoretic, the space is significantly smaller. And there's not necessarily, what I say, a natural way to combine them together. For example, if we're entering shares into the computation, then there are going to be reconstructed modules that we use for the field, or more increasingly, this is the ring these days, right? Even the structure of the computation is going to be different. So if you think of discrete logarithm-based constructions, say the exponents are, which we're going to be using in commitments, or, say 250 bits, which is way longer than what we use, say, when we create secret sharing, even if you want sort of protection against active adversaries, then the statistical parameters are still going to be much shorter than the same 250 bits. And this is not going to be field anymore, right? This is a ring. This is another difference. But what we have today is that when we have multiple messages, many messages that are being entered into secure computation, you can either do this efficiently in sublinear time for the number of messages, or if you actually want to sort of combine short space with a longer space, that's also possible, but it's becomes linear work, right? So this is the current state is that you can either do one or the other, but would like to be able to merge and do them together. All right, and I also would like to mention public verifiability, which is something can be desirable. Desirable when we work with, say, certified inputs, but it's not necessarily natural as a part of secure multi-party computation techniques to do that. And this is also just room for thought. So this is one component. Another one that I would like to mention is the choice of the function itself, right? When we look at standard definitions, they'll say, given a function, I'm going to evaluate the function. And then during the evaluation itself, we want no leakage, we want no information disclosure, but everything that you produce as the output is fine, right? So here what we say that during the computation, there is no leakage, we eliminate all of that. And what we produce as the output is good, right? That's authorized leakage, we'll take that. But the question here is that, do we look at the output, right? How do we choose the function itself to understand whether this leakage disclosure at the end is what we want? So in this case, in this figure, this is the function itself in the middle, right? Say that this is the component that we would like to look at saying, is this what we want to do? And so from that point of view, the choice of function, which functions can be or should be related in this framework, is not necessarily something that's been explored enough. And I would like to look at this. Clearly, the goal is that when you run the computation with private data, you shouldn't just be able to recover the inputs exactly from the output itself, right? So we probably mentioned this identity function where I enter my inputs and I immediately output them as the result. Clearly, this is not suitable for us to use in this context. But the question is, how do we measure? How do we decide that this particular function is good and this one is not good, right? So we can sort of think in terms of the notion of non-invertibility, right? So if I can recover the input directly from the output, clearly this is not good. But if I cannot do this, what is the measure of goodness, right? So if I have, say, 10 different options for the input, looking at the output, is this good enough? How do we measure? There is not necessarily a good metric in this case. And I think that becomes important when we actually want to deploy these functions, when you go to explain to people outside of the community, like, we can do this securely, but if we don't understand how much we're disclosing from the output as a community, that it's harder to convince other people that that's secure, okay? And what I'd like to do is to give an example, say, of working with medical data in compliance with law, something like HIPAA law. So if I go to, data guardian at a hospital, and I'm trying to explain, right, what they want to know is this compliant with the regulations or not? Is it HIPAA compliant? And if we think of the computation law, we're just disclosing the most effective treatment for that condition, it naturally seems that it actually wouldn't leak information about patient records. But do we know that it's the case, right? Can we measure this in some way? And so from that point of view, we'd like to understand better under what circumstances the function itself is suitable for the context of secure multi-party computation. and when it's not. And so, um, well, I think that's so. This is something I would like to go into a little bit more detail at the end, right? So I'm gonna stop here. I'm gonna switch to like a different topic, and we'll return to that because I would like to talk a little bit more, in this topic. All right. And the third component that I would like to mention here is linked computations. And so what I mean here is that typically we write a definition saying that, well, we're going to take the inputs, we're going to compute on those inputs, we're going to deliver the outputs to where they're supposed to go, and we'll go home. So this definition is standalone, does not necessarily mean that the results will be used somewhere else, right? Or it's not necessarily natural for something like we have data that's persistent and you issue queries to the private data set over time. And so in this case, what we would like is maybe somehow expand the notion of secure computation, right? Incorporate that into definitions. There could be multiple executions, different phases. But when it becomes more interesting is that when the computation participants change, right? The parties who are on the computation or nodes are not going to be the same anymore, and they may be providing new inputs into the computation. So I would like to demonstrate this on this figure. So we run one computation, and then the outputs or some information was delivered as the result of the first execution, and it's going to also be used by another computation that happens afterwards that is somehow related. And the example in the context of which this I ran into was the biometric authentication. So in this setting, what we'd like to do is if you have biometric data, clearly it's sensitive. We don't necessarily want just store it in the server, so we're going to store it in a protected way. So there will be two different phases, right? When the user first registers, and then when they're going to come and authenticate to the server. But so the way we've done this is that we take the biometric, we split it into shares that reside across two different servers that are going to be assumed to be non-colluding. And then at authentication time, we're going to get a new biometric that is going to be compared with what was already stored in the servers. But this is the place where the computation participants change, right? Because when the user comes in saying, well, yes, I would like to authenticate, we have to allow for the possibility of malicious user trying to impersonate somebody else, so it may not be the same user anymore. And so in the context of this illustration, right, we have registration and authentication, but then at authentication time, it could be a different user who submits malicious input. They may even conspire with one of the servers who may try to deviate from the computation, use wrong information in the attempt to frame the original user. Okay, so the original user left their traces in the system. Their biometric is encoded based on what is being stored, and this can be the target of attack. So if we look at these two phases separately, we won't be able to capture the fact that the privacy of the first user can be compromised through a later computation, right? And so, in this case, what we did in our case is that we look at definitions and we generalize them. So instead of just saying this is a computation that is going to be done once, now there could be multiple phases to the computation. And the first one is going to be normal, like the way we would always do this, right? But in this case, if the sort of later phases are run by different participants, that we need to explicitly say phase one has this participants P1 through Pn. Phase two may have different participants in the computation. And another issue here is that after the first phase, we have some memory in the system, or if you say maybe there were outputs of the first phase, and then they're not explicit inputs into the second phase, but they become auxiliary inputs into the second phase, and there's more than other phases as well. And so then when you say that your solution is secure, what happened in our case, we would need it to enumerate different instantiations, right? It's possible that we're going to have authentic user at registration and authentication times, or it's possible that it's going to be authentic user at registration and an imposter at authentication times, and you'll need to be considered like different combinations. So this is a work that is going to appear later this month, and if you're interested, you can take a look. Sort of this is focused specifically on biometric authentication, but the definitions are general. They're only going to apply to any kind of secure computation that you might want to use. All right, this is where we get as I would like to wrap up the first component of the presentation. And the sort of the message that I try to convey here is saying that we oftentimes focus on how to do the computation for good reasons, right? That's important to keep doing this work. But somehow, if we want to see sort of more deployment of this kind of techniques or integration them into real world, it seems that other components also deserve our attention. And I guess the message that I want to send is that consider these topics as well. And for the second type of the second half of this presentation, what I'd like to look at is the topic of the choice of the function, right? How we sort of pick the function, how we decide whether the function is good enough to be used in this context. And so where we started is we looked at a metric, right? So the idea is that we sort of pick a particular function, and each function is going to be different, and say, can we measure information disclosure, from the inputs from the outputs, right? So we're looking at output privacy in this case, and there's the idea is that the measuring is the first step. If we can measure, then we cannot say anything meaningful about information disclosure. And once we've measured, we can decide, well, if this was sufficiently small, that's good enough. If it wasn't sufficiently small, then we can make decisions in terms of, well, maybe we should change something. We can either say modify the function itself, we can introduce noise, doing differential privacy, or maybe we can change the setting, right? For example, set it up in a different way so that the information disclosure can be reduced, which will be the case for what I'm discussing here. So we've picked the notion of entropy as a sort of well-established notion of uncertainty that we can use, in this case. And so we use Shannon entropy for discrete inputs and differential privacy for continuous inputs. But in general, you can use different notions of entropy. We, for example, also looked at min entropy, but the trends were similar. What is good about using the regular notion of entropy is you can go further in the analysis. And that allows us to derive analytically, formulas and do analysis that way, which wouldn't necessarily possible if we used a different metric. So the definitions that we looked at were due to Haft and Koos that looked at, and I guess it's similar context. We have two sort of metrics that we can use, or two notions of security, and I'll explain what they are. So they're called attackers weighted average and targets weighted average. We'll see the way they're formulated. So before we continue, I would like to say that at this point, I would like to look at secure computation as a black box. So it's somehow evaluated, right? It doesn't matter how it's evaluated. And in this case, the parties we care about are input participants. So we have inputs coming from different sources. There is, say, a group of participants are going to be the adversary or the attacker that would like to learn something about a different group of participants for the target. And everybody else who is neutral is going to be a spectator, right? So we have these three groups, and it could be one individual, can be more individuals, depending on what the goal here is. And so then, during the sort of relation, there's going to be certain like random variables that model the party's input, and we're going to instantiate them with the particular values. And so the way we would formulate this is that when the target, when the target sort of looks at this from the target's point of view, I'm going to enter certain input into secure computation. And I would like to understand how much can an adversary learn about me this particular instance, right? So in a way, everybody is going to get the output from the function, and how many different ways can adversary set their input and receive certain output combinations and see what they can learn about me. So from target's point of view, I know the input that I have, right? And sort of I'm trying to decide should I enter this computation or not based on what the adversary can learn about me. And the attacker's point of view is different, right? So the attacker says, well, I'm going to enter some input into the computation. If I try this input, what can I learn about the target based on the same information? These are combinations of the outputs that you observe, right, and what you can deduce about the victim. Then the adversary says, well, maybe I'll try a different input. So the idea in this case is that they can find a particular input that is going to give them the greatest advantage. Right? So if we look at it this way, then target basically target supposed to honest, right? Decides should they participate or not based on how much information disclosure is going to be about my input. But the attacker is different, right? The attacker doesn't care about correctness. They can try different inputs and see which input is going to be the best for their strategy. And so what we've decided is that the attacker's viewpoint is better if we're deciding, well, it's more informative if we are deciding which notion, if we're deciding whether the function is suitable or not, right, for secure computation, that we should take the adversarial view for a couple of different reasons, right? The target's input is not known at the time when you design your solution, right? So you cannot necessarily rely that. And also from the target's point of view, if the target says, well, if I enter this input, it's good enough. If I enter different input, it's not good enough, and I'm just not going to participate. The fact that the target did not participate immediately leaks some information about them, about their inputs, right? So from that point of view, if we're deciding ahead of time, should we run this computation or not, we'd like to take that adversarial view. And so the example that I would like to look at is very simple. This is the average computation. And maybe I'll ask this audience, so how many people are familiar with the Boston gender pay gap study? All right. Well, it's a good number of people here. And so this is the example that we've picked. I'm gonna talk about this more, but before we continue, I just wanted to also show the formulas that go into the computation, right? So to get to either target's or attacker's view, we first formulate the joint weighted average entropy. And so if you look at this case, so what we have is, well, it's weighted average entropy. We take the entropy. In this case, what we want is to learn something about the target. And the adversary already, entered some input. We got some output. And the question is, how much can we learn about the target? And the joint weighted average entropy is formulated when you have fixed input for the attacker and the target, right? And the capital letters are the variables, and the lowercase letters are instantiations of those variables. And so, like, we have the entropy remaining after the computation, and we basically add them all together, weighted by the probability of that output happening. So if the output is more likely, right, that the inputs are also, more likely. And then we take this joint weighted average entropy for the target's view. Basically, the target enters certain input, right, and we're going to additionally do the weighted average entropy based on the probability of each attacker's input happening, right? So the target's weighted average has the target's input fixed. The attacker's weighted average has the attacker's input fixed. And in this case, what the attacker is going to be doing is entering one input and computing this value, entering different one, computing this value, and see which one is going to be the advantageous for them, and this is what they're going to enter in the computation. All right. So now I'd like to move on to the case of the average salary computation that was inspired by the work that was done, in the city of Boston. So, in that case, the idea was that the city wanted to measure the gap, the pay gap by gender. And this actually was, Women's Council was involved, and they want to know for the same profession. This is, the average male salary. This is the average female salary. But then nobody wanted to be responsible with collecting data that is sensitive from a lot of different businesses, and they turned to secure a multi-party computation, which was done in collaboration with the researchers at Boston University. So in that case, the computation is so simple, right? What we're doing is the average, but we can further just say like this is a sum. If you know how many participants are entering their data into the computation, then the average is the same as the sum, so we can treat that as the sum of the computation. So I'd like to look at these definitions for that particular function, and this is uniform distribution just for simplicity, where we have inputs between 0 and 15. And in this figure, you'll see that the straight lines are the adversarial advantage, or the information that they. So this is what I should say, uncertainty that is remaining after the computation. All right, so the straight line will be, we have like one spectator, we have one target, one adversary, and one spectator. So the original entropy in this case for the target was 4 bits. And then depending on how many spectators we have, the straight line is the adversarial view after the participation, right? After the computation, when they learn the result. And so you see, sort of naturally, the more people participate, the better protection you're going to have. And so that line keeps increasing as we add more people. And what's interesting in this case is that the adversarial view is constant, independent of their inputs, which for this function makes sense. That's not always the case, but for this function, what this means is that they can always remove their contribution from the sum, right? So the view with their participation, without their participation is the same, and it doesn't change. And in some way, it's good. It's easier for us because then we know that it doesn't matter what the adversary enters in the computation. That's not going to impact the advantage that they have. For the target, that's different. And you see from the target's point of view, if I'm closer to the average, right, and I'm closer to the middle, I have a less information disclosure about my inputs than if I have some extreme inputs. But, we still would like to proceed with the adversarial view as we plan the computation, right? Before we start, we need to decide, should we proceed with this or not? All right. And so we've sort of looked at this problem, extensively. We looked at a couple of continuous distributions, a couple of discrete distributions. We have uniform and Poisson for discrete, and normal and log normal for the continuous distribution. And so the fact that we're using Shannon entropy or differential entropy allowed us to analytically derive all of the formulas, so we don't have to go enumerate all of the possibilities for inputs and outputs, right? So we don't have to do brute force search. And so in this case, what was interesting is that how similar all of them were. And really for salaries, if you look at salaries, log normal is what this is what you're going to want to use. And for log normal, we have certain parameters that are typically used for modeling salaries, and we try to calibrate others so they're going to have similar parameters. But what we got is the following figure. So we have four different distributions. We have uniform, Poisson, normal, and log normal has only one set of parameters on which we instantiated it. But you see the top line is the initial entropy of the target prior to participation, and this curved line is the remaining entropy after participation based on the adversarial view, and the scale here is the number of spectators. As you increase the number of participants, you'll see that the gap between the original and the remaining shrinks very quickly, all right? And what was interesting, we wanted to validate basically the intuition that Boston University researchers had, that they basically suggested to run this computation when you have at least 5 participants, right? But in this case, actually 5 is meaningful because even with 5 spectators, you're allowed to shrink the participation, the gap between the original entropy and what's remaining, right? The loss, to a very small margin. So I would like to look at them more closely, and this function in a way was special because we're able to get very nice distributions that are basically all the same, very close or the same, and this is different for other functions. Now we're looking into additional function that's not the same behavior, but so what this shows is that this is for uniform distribution, but it shows the information loss, right? Entropy loss. So we had some original, and then after the computation, that got reduced, so that models difference. So if you have only a single spectator, right, the information disclosure is always less than 1 bit, and it shrinks significantly. But what's interesting, it doesn't matter what kind of parameters we pick for the distribution, it's identical. So on the left, this is absolute loss, and on the right, we also plotted relative, but relative was just to convey to other people who don't necessarily understand the notion of entropy, is that you had some original uncertainty about your input. And suppose that you don't want information disclosure to be more than 5% or 1% of the original. And then, we'll plot this relative and say, well, for example, if you want at most 5%, then you need 5 spectators, right? Or 6 people together with a target. If you want at most 1% of disclosure, you say we need 24 spectators or 25 participants together with a target, right? That will allow us to make decisions based on sort of intuitive notion of how much information is being leaked about a participant during the computation. All right, so if you see, these are different distributions, but they look, very similar. The behavior on the left is that the absolute information disclosure is the same for all different distributions. So this is normal. Log normal is only 1. And then we try to compare them across different distributions and saying we sort of pick parameters that would be similar to log normal. The initial entropy is like a little bit more than 3 bits in this case. And when we sort of overlay them one on top of each other, you see that even across different distributions, they're very close. So when we have absolute and relative, they remain very similar, right? So once again, this is somehow only for the sum function that is very simple, and it's not necessarily going to generalize if we look at other functions. All right. So then the next thing that we wanted to do is to look at multiple executions. So if you do this once, right? In the case of the Boston gender pay gap study, they ran it 1 year, then they ran it another year, and they changed number of participants. They recruited more companies. It was actually quite a bit bigger experiment. And so we wanted to understand what happens in this case, and this one is actually interesting. So in this case, we assume that the experiments are close to each other in time enough that the inputs don't change. Okay? So far, also all of these data are for identically distributed inputs. And then since then, we also looked at not identically distributed. So one company's salaries maybe not, you know, following the same distribution as in a different company. But so what I'd like to show you one interesting plot. So this is, basically participation for different number of spectators. I think on the left we have 6 and on the right we have 25 or something to this extent. That's just, you will show that the scale shrinks a little bit. So the first dotted line on top, this is if I participate. There's one experiment is run and I participate, right? So this is, well, actually, the red is going to be the initial entropy before my participation. So it's slightly over 3 bits. And then the green line, if there's only a single experiment, right? So you see that there's a gap of a fraction of a bit. And then there's 2 different lines that where we model either I participated the first time, but not the second time, or I can participate the second time, not the first time, or I can participate twice. And so in this case, we want to protect all of the participants. If I participated the first time and I left, right, so it's beneficial for me that the difference in the 2 different sets is significant. If I'm the only delta, my salary can be computed, right? And for people who participate the first time and then the second time, right, the story is the opposite. Basically, if the entire set changes and I'm the only delta, then my salary can be discovered. So what we'll look in this figure is actually the blue line is people participating twice, and the pink would be if you participated only once the first time or the second. But you'll see that this pink is actually goes down to 0. All right, so we just didn't plot it because then you couldn't see the behavior of the function. But in this case, you'll see that the parties who participated once or twice, there's the conflicting behavior between them, right? Someone get better protection if the sets don't change, and others or change little, and others get better protection if the change are very different. And so I forgot to mention that here on the bottom we sort of plot the difference of the sets, right? We we have there could be all the same, there could be all completely different. In this case, there's a divergence of different desires in this case. So the best point is in the middle, right? So the bottom line is that if you run this computation once and you run it the second time, you want about half of the people to be staying there, right? And others to be recruited and you. That's going to offer the best protection. And in this case, you can compute basically the information disclosure is a little bit more than with a single participation, and then you're going to use this as the point to decide, should we, how many participants should we recruit if we want to run this twice. All right. So I think, I'm getting to the end of this, presentation. And I wanted to say is that, for this particular study, this is also something that's going to appear, this month. And we have the published version, but also have an archive version that is longer. It's going to also have like more than, 2 experiments and some, additional insights that I'm including here. But the interesting part is that the, in this case, the average computation was so simple, but there's still interesting insights into what we can do. And we can even give sort of suggestions for how to set it up in practice, depending on what kind of information disclosure you want to tolerate. And when you have repeated experiments, then what you need is sort of maximize the overlaps between different subsets of participants. That will be true also if you do 2 experiments, if you do 3 pairwise overlaps. All right. So, all right. So, to conclude the entire talk, It's, you know, from my point of view, there's still like interesting different directions that we can explore as a community in the space of secure multi-party computation. And one of them was what I talked about, information leakage from a function. And I think this is in some way people pursue for some types of functions. For example, when we talk about neural network training, right? We understand that it's not safe to train a model on private data and disclose that. So this notion of membership inference attacks, which in some way is trying sort of to um, you know, come close to, you know, what we're looking here, right? Understanding when it's safe to release the output and when it's not. But from my point of view, I think we want to analyze more functions and understand when they're suitable, when they're compliant with regulations, and what we can do in that case. All right. Thank you for your attention. I'll be happy to take questions.